We are doing theoretical and experimental probability. So let's zoom in and see what this is all about. So whenever we have a dice and we roll our die, one die, right? We've got 6 sides it can land on, right? So the probability that it lands on a 5, right? Since there's 6 different sides, 1, 2, 3, 4, 5, 6, right? The probability that it lands is going to be a fraction. What you want to have happen divided by the total things that can happen. So if I want it to land on a 5, there's only one 5 on this dice. So there's only one chance that it can land where I want it to. And there's 6 sides it can land on. So the probability of rolling a 5, right, would be 1 chance out of 6. Because there's just one 5 on there and there's 6 sides on the cube, right? What's the probability of rolling a 3? Roll a 3? Would be the same because there's only one 3, and so that would be 1 chance out of 6. Right? That's all there is to it. Look at this. This is a spinner. Right? We got red, blue, green, yellow. Right? So we have 1, 2, 3, 4 different sides. Right? 4 different sides. So the probability, if I could spin this little spinner here, round and round and round and round and round, the probability that it would land on a red would be 1 chance out of 4. Why? We want it to land on the red after I spin it. Well, there's 4 parts, and they're all equal sizes, right? This is 1/4 of the circle. This is 1/4 of the circle. So the green's 1/4, the yellow's 1/4, the red's 1/4, the blue one's 1/4. So everybody has an equal chance from when I spin the spinner round and round and round, it lands red, right? So the probability of something happening is you always start with a fraction. And then once you make it into a fraction, then you can go ahead and make it into a decimal or a percent. So I know 1/4 of the time, if you don't know, 1/4 of the time, 1 divided by 4 is 0.25. You see that? 1 divided by 4 is 0.25. So this would be the same thing as saying 25% of the time it's going to land on red. All right? 25% of the time it's going to land on red. What about this, the dice one? When I roll a dice, remember there's 6 sides, 1 chance out of 6. Well, if I do 1 divided by 6, look at that. That's 1.67. So that's 16.7% of the time it's going to land on a 5. 16.7% of the time, that's 1 chance out of 6, it's going to land on the 5 when I roll it, right? Or what if it's a 3? Same thing, 1 chance out of 6. You know, and here on this one, what's the probability that it lands green? Well, 1 chance out of 4, right? So that's assuming that everything is the same size, all the little pieces are the same size, and that the spinner spins evenly. It's not rough on one side and smooth on the other side, so it always stops one place, you know. The dice, we expect the dice to not be heavy on one side, all the sides be the same weight, so whenever you roll it, it has an equal chance. So if one side was heavier, then it would always land on that, or it would more often land on the downside, the heavy side, you know, and so you don't want that. So that's theoretical. Let's look at an example of experimental. So here I've got this guy right here. This is a table that shows the spinner experiment, that one we just talked about. There's 4 sides, there are 4 colors, and they're numbered 1, 2, 3, 4. So I got red, blue, green, and yellow, right? 1, 2, 3, 4. And when this person was spinning the spinner, look what happened. The red only came up 6 times, but the green came up 19 times. Uh-oh, what's going on? Is it lopsided? Is the spinner heavy on one side? Is it the circle rough over there that it always lands on the green? You know, what's going on? Well, this is called experimental probability. And so when you actually spin, when you think about spinning the spinner, it's supposed to be 1/4 of the time in each color. All right, it's supposed to land there exactly 1/4 of the time. But whenever you actually do an experiment, sometimes it doesn't work out that way. Right? So here, let's do this. What's the experimental probability of spinning and landing on a 4? So spinning and landing on a 4. Well, first we have to add all these numbers together. So we need to know what the total is. So let's go ahead and do that. 6 plus 11 plus 19 plus 14. Turns out there's 50. So the total of this is 50. So if I'm looking at spinning a 4, I would have 14 chances out of 50. 14 chances out of 50 of spinning a 4. Spin a 4. Right? How do I know that? Because that's what they did. Now, 14 out of 50. 14 divided by 50. That's 28% of the time. 28% of the time it's going to land on the 4. Now remember, theoretically, if all the colors are the same size, it should land there 25%. Right? Let's look at this one. Spinning a number greater than 2. Well, greater than 2 means you spin a 3 or you spin a 4. So let's write that down. Spin a 3 or spin a 4. Right? That's what they're talking about. When they say spinning a number greater than 2, they're saying spin a 3 or spin a 4. Oh my goodness. Well, let's look. 3 is 19 out of 50. And 4 was 14 out of 50. So when we add those two things together, we get 33 out of 50. Right? So what's the probability? That would be 33 divided by 50, 66%. This is 66%. Right? Now check this out. When you have a spinner and you want it to land on this one or this one, right? Remember, if this was theoretical, this would be 1/4 and 1/4. So this would be 1/4 and 1/4. So 1/4 plus 1/4 would be half the time. Half the time we would expect it to land here. 50% is what we're talking about. But look, it actually landed there 66%. Now this doesn't necessarily mean that something's wrong with the spinner, right? It's just the way that things happen. You know, it's never a sure thing. So if we did this experiment again, we would probably get it landing different numbers all the next time we do it. You know, this could be 19 and this could be 14 and this could be 11 and this could be 6. You know, it could be all mixed up just because of the way we spin the spinner. It doesn't mean that something's wrong with the spinner. It just means whenever you're experimenting, sometimes it doesn't work out to be exactly what you expect. And you've seen it before. When you flip a coin, you got 50-50 chance to land heads or tails. So you'd expect if you flip it 3 times or 4 times, you'd expect it to be 2 heads and 2 tails if you flip it 4 times, right? But sometimes you're going to get heads, 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 heads. And sometimes you'll get tails, heads, tails, tails, right? And so it doesn't always come out to be 2 heads and 2 tails when you flip something 4 times. That's just the way it is. Experiments, that's the way they work. Okay, let's look at this one. This one is important. Okay, so we're looking, this is on your book, in your book, page 491, if you want to look in your book. This is this. So let's look at, see what it says. It says that we have a red dice and a blue die, right? A red one and a blue one. And so this is all the things that could happen. When I roll my two dice, one red, one blue, I could get a 5 on the red one and a 1 on the blue one, right? Or I might get a 4 on the red one and a 3 on the blue one. Or I might get a 6 on the red one and a 6 on the blue one. Or I could get a 2 on the red one and a 5 on the blue one, right? So these are all the possible things that could happen. So there are 36 things that can happen there, because 6 by 6, there's 6 sides on the red dice and there's 6 sides on the blue dice. So 6 times 6 means there's 36 possibilities that could happen, right? So here they said, what's the probability that when you add them up, the probability is 10, the sum is 10, right? Well, if you roll these two, that doesn't add up to be 10. That doesn't add up to be 10. See, these are the two here. 6 and 4, 5 and 5, 4 and 6, right? The red one's 6 and the blue one's 4, or the red one's 5 and the blue one's 5, or the red one's 4 and the blue one's 6. There's 3 times out of 36 that it could add up to be 10. So that would, when you reduce your fraction, that would be 1 chance out of 12. 1 divided by 12 turns out to be 8.3%. So we would expect this to happen. Where can I write that? 8.3% of the time. That's what we're saying. You can't even read that. Huh. We'll write it on this. Then we can read it. Here we go. 8.3%. So we said 3 chances out of 36, which was 1 chance out of 12, which turned out to be 0.83, that decimal right there. So when I move the decimal, that's 8.3%. So that's not very often. I would not expect to roll a sum of 10, because 8% is not very often. Oh, I forgot to show you that. Over here, see, the bigger the percent, the more likely it is to happen. So here's 100%. Let's zoom in on that. Zoom, I said. Zoom, zoom. There we go. So 100%, it's guaranteed to happen. Like the sun's going to come up tomorrow, that's 100%. The probability of the sun coming up tomorrow. So whenever the percent is bigger than 50, then it's more likely to happen. This is likely to happen. And then if it's smaller than 50, like 25% of the time or 8.3% of the time, that's not very likely to happen, right? The smaller the percent, the less likely it is to happen. So something that's impossible to happen, when we go to the moon, we'll find it's made out of green cheese. The probability that the moon is made out of green cheese, that's 0%. Why? Because we know it's made out of dirt and rocks, right? With a cream cheese center. No. just dirt and rocks. So it's the probability that it's made out of cheese is 0, right? So there's some things that are impossible. There's some things that are guaranteed, like the sun coming up. But then when we roll a dice or spin a spinner, then the probability of something happening is going to be in between here, one of these little percents. And so the smaller percents, not very likely. The larger percents, yes indeed. Okay, so let's go back to this question here. Where was I? I was right there. I had it all set up. And so here's my next question for you. What's the probability that it subtracts to be a 3? Well, look. Now we're trying to subtract to be a 3. So let me get something to circle with here. We got it. Let's get a color that really shows up like green. Okay. Subtract to be a 3. So let's see. We could choose, we could get 6 minus 3. That would subtract to be a 3. 5 minus 2, that would subtract to be the 3. 4 minus 1, that's where the red one is bigger than the blue one, right? But look over here. Here, 4 minus 1, the blue one's bigger than the red one. Still subtracts to be 3. That one subtracts to be 3. So look, there are 6, 1, 2, 3, 4, 5, 6 different ways to subtract to be a 3. So remember that there's 36 possibilities. When I roll my dice, there's 36 ways it could land, and only 6 of those ways is what I want to have happen. I want it to subtract to be 3, right? So, that means that's 1 chance out of 6 if I reduce that fraction. And I think we figured that out just a minute ago. 1 divided by 6, or 6 divided by 36. That turns out to be 16.7%. Move the decimal twice, 16.7. So it's more likely to get something that'll subtract to be a 3 than something that'll add up to be a 10, because remember, this was only 8%. This one turned out to be 16% of the time. Twice as likely, right? Let's look at a couple here. So maybe we can erase all my stuff here for a second. Get rid of all my numbers. Use a different color even. Yeah, there we go. All right, so what's the probability that the sum is a 6? The sum is a 6. So I have to look, when I'm looking for things to add up to be 6, how can that happen? Let's change my color. I'll get red this time. I think red shows up better. Oh, red, yeah, there we go. Adds to be 6. So if it sums up to be a 6, well, 5 and 1 adds to be 6. 4 and 2 adds to be 6. 3 and 3 adds to be 6. 2 and 4, 1 and 5. Right? So when you add, you're going this diagonal this way. When you subtract, you're going diagonal this way, right? Subtraction was this way. Addition is this way. That's what we're saying. So these two add up, these two add up. So there's 5 ways that'll add up to be a 6. So if the question that we were doing was, what's the probability that I roll 2 dice and I get it to be 6, we just said that was 5, right? 1, 2, 3, 4, 5. So 5 chances out of 36 is the answer. Now you can leave your answer as a fraction, or you can change it to be a decimal. 5 divided by 36. That turns out to be 13.9%, almost 14% of the time it would subtract to be a 6. So we're going to say 13.9%. Right? Now some things are impossible, like this. The difference, that means you subtract. You subtract to be a 6. There's no way to subtract to be a 6. If the biggest number on the dice is 6 and the smallest number is 1, right? 6 and 1, when I subtract the biggest number from the smallest number, that's 5. There's no way to get a 6, so I can't do this. This would be 0%. There'd be no way to subtract. And how about count all the times that the red one is bigger than the blue one? Ooh, now that's tricky. Well, you just have to count. That's all there is to it. So let's do that. Let's erase, 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 erase all this good stuff, right? Get rid of it, get rid of it, get rid of it. And there's all this. All right. Now then, we're looking for when is the red one bigger than the blue one. So this is at the top of 491. It's probably easier for you to see it on your page than on mine, but let's look. When is the red one bigger? Well, how come it's so reflective? Let me get rid of that. Oh, look how beautiful that is. Okay, red one's bigger. So the red one is bigger here. 6 is bigger, 6 is bigger, 6 is bigger. Okay, so the red one's bigger all of those times, right? 1, 2, 3, 4, 5. So there's 5 times when the red one's bigger. And then here, the red one is bigger 4 times. And here, the red one is bigger 3 times. And here, the red one is bigger 2 times. And here, the red one is bigger 1 time. And there, the red one's not bigger, right? So 5 plus 4, 9, 10, 11, 12, 13, 14, 15 times when the red one is bigger than the blue one, right? And that was the question, right? When is the red one bigger, right? When is the red cube greater? And we just added those up. That was 15 chances out of 36, right? What is that? So first of all, you can't leave it a fraction if you can reduce. So let's see if we can reduce. 15 divided by 36. Remember, if you type it in your calculator and you want to reduce, you just hit the math button. The top thing in the list is fraction, and it'll reduce your answer. So that's 5 chances out of 12. 5 chances out of 12. So 15 divided by 36. Why is all this stuff in my way? 15 chances out of 36. Get rid of all these boxes. There we go. 15 chances out of 36 is, if we move this decimal, 41.7% of the time, right there's the percent, 41.7% of the time, or 5 chances out of 12, that you would get the red one being bigger than the blue one. That's what they want to know, right? We can do that. We can do that. Now then, there's something else you need to know, and that is in math, there's something we call a complement. And it's not like saying, hey, you're beautiful. That's a compliment in English. But in math, it means something else. So let's see if we can read this question right here. Not unless I zoom in. There we go. There we go. So the problem here says we got the game of Battleship. So if you've ever played Battleship, what you know is you've got a box there that has 100 holes in it. There's 100 holes. And then each ship covers up a certain number of holes. So the destroyer covers 2 holes, the cruiser covers this, the carrier covers 5 holes, right? And so if we add all these together, let's see, 5 plus 4, 9 plus 6, 15, 17. This is 17. When you add them up, the sum is 17. So there's 17 holes. The ships cover 17 holes, right? So let's read the question. So we solved this, so we know that there's 17. So let's zoom in a little bit. What's the question? What's the probability that the very first shot misses all the targets? Misses all the targets. Well, we know that the targets cover 17 out of 100 places, right? So 17 out of 100 are covered with the ships. But we know that if we take 100 minus 17, which is what they should have showed you right there, 100 minus 17, that would leave 83 empty spots for the person to shoot at, right? There's only 17 filled spots. So 83 empty spots. So the probability that the very first shot misses is 83%. 83 out of 100. That's called a complement. Whenever you take the total and you subtract the ones that you know about, then what's left is called the complement. So here, let's do another example with complement. Let me get my paper here. Whoa, it's all torn up. There we go. Put that, hide all my answers from you. How about that? Here we go. Let's do another one with complement. Okay, so there's 25 students in study hall. So that's what we're talking about right now. There's 25 students in study hall. And they tell me right here that 6 of them are learning French, and 12 of them are learning Spanish, and 3 of them are learning Japanese. Now we need to add all those up so that we can find how many total are there, right? So if I add this, that's 15, that's 21. So there's 21 kids studying foreign language in study hall, right? That's the question. Or no, that's not the question. The question wants to know how many of the students are not learning a foreign language. How many are not learning a foreign language? So I know 21 are. I know that there's 25 total. So 25 minus 21 would be 4. And so the probability that I go in there and I pick a person out of the class and I know that they're not studying foreign language, there'd be 4 chances out of 25 that I could pick a person that's not studying a foreign language. So that's a complement. When you take 100%, which would be 25 kids, minus the ones that you know, which is 21 kids, then that leaves 4 chances out of 25 that I would actually pick a person that is not studying a foreign language. What are they studying instead? Well, I hope they're studying math, right? Yeah. That's the ticket. That's the ticket. One more and we're done. One more and we're done. Here we go. Boom, boom, boom. All right, so we've got this. Whoops, the answer is right there. Oh, well, we won't look at the answer, right? You're not looking at 35%, are you? Okay, so let's erase. We'll erase all this cradola like that. And then maybe we'll steal something so we can. There we go. I don't remember it said 35, huh? All right, so here we've got a big square, right? This is 9. This is 9. And then down here, this is also 9, 3 by 3 by 3, right? So there's a big square, and then there's a triangle inside the square, and then there's a rectangle inside the triangle, right? And the question they want to know is what's the probability that, like if this was a dartboard and I threw my dart, what's the probability that it would land in the triangle, in the shaded area, in the shaded part of the triangle. It could land here, could land right there, could land right there, right? The question is, what's the probability that it lands inside the triangle but not inside the rectangle, right? So we want the shaded area. So what do we have to know? We have to know the total area, because remember, the bottom of the fraction has to be the total. So the bottom is going to be the total area. Where could the dart land? Well, that's everything in this big square. So you know how to find area, right? This is 9 wide and 9 tall. So 9 times 9 is 81. So the bottom of the fraction is 81. Now, we got to figure out the area of a triangle. So you remember, a triangle is base, that's 9, times height, that's also 9, right? Divided by 2. So 9 times 9 is 81, divided by 2, that's the area of the triangle. So the area of the triangle, right? That's the area of the triangle. 81 divided by 2. So that's 40.5. But it can't land in this piece, so this is a rectangle, and you know this is 3 by 4, 3 wide and 4 tall. So that would be 12. 3 times 4. 3 times 4 is 12. That's the area of the little rectangle, right? So what I have to do is I have to subtract 12 from 40. So 40 minus 12 is 28. You can see it right here. 40.5 minus 12 is, whoops, I said 4.5. That doesn't work. 40.5 minus 12. There we go. 28.5 is what the area is that we're trying to find, right? What we want it to do is we want it to land in the shaded area. This is the shaded area right here, 28.5. So, if I do 28.5 and divide by the total, which was 81, because the dart could land, if I'm throwing darts, it could land up here, it could land in here, it could land in here. What's the probability that it lands inside the shaded area? So the area that you want goes on top of the fraction. The area that the total place it could land is on the bottom of the fraction. And then, if we go ahead and do that, 28.5 divided by 81 turns out to be 35%. Hey, remember that? Let's look. 35%. Yay! Oh, you can't see that. There we go. 28.5 divided by 81. The area that you want divided by the total area. Okay, you should be able to do today's homework without any trouble. Bye-bye.